today I'm going to actually not be present to discuss and share my knowledge. I mean, the experience I gained from the industry doing these concrete repairs, and it's kind of a discussion time. Then I can share my knowledge and I can get the feedback from you all. So actually, this is going to be the for the concrete repairs in the technological wise. We have to check that is what are the available technologies and what are the evolvements and advancements during the course of the material developments, so on. So we'll discuss with these topics. In this, my content would be like first we have to identify what are the concrete defects, the concrete repair, crack injection. I'm going to talk about and discuss about strengthening of structures with fiber reinforcement polymer, FRP, and underwater pile repairs, and job site applications like what we have done and industry has gained so far. So first we discuss why concrete. We all know next to water, the concrete is the most abundantly used construction material on earth. So it's very cheap, economical, and in terms of cost per ton, it's very cheap. It's also one of the most convenient and versatile construction materials. Moreover, when made properly, we can do wonders. Very durable. So we all know that concrete is good in compression but weak in tension. That's why we need the reinforcement to be introduced. So the principle of reinforced concrete is that concrete is strong in compression, weak in tension, as we discussed, invented by Romans, but first successfully used in 1854 for the steel rods. So when it comes to concrete defects, we can identify in our job sites honeycombs due to lack of poor curing or compaction. Cracks, of course, you can see the slide. And hello? Hello?
Long press?
And
hello, yes, you can continue.
Yes, so these are the honeycombs like we discussed about that due to lack of compaction, the poor workmanship, and of course cracks. And you can see this the ingress of, I mean, like we all know that is the concrete is porous. So we normally designers allow like 0.2 millimeter cracks. Even with the 0.1 millimeter crack, it's like the ingress of chloride ions and other carbon dioxide is possible. So like, let's say if you have a 0.1 millimeter crack, even 500,000 chloride ions can cross its width. So it's like the concrete, the cracks is very vulnerable. I mean, like very critical to the structures. So we talk about dry shrinkage cracks. Like it's the cause of the dry shrinkage is like loss of water causes change in volume. So all the cementatious materials, we have I highlighted this. All the cementatious materials tend to shrink. So this dry shrinkage mechanism, like restraint introduced tensile stresses. So it's obviously cracks is actually generated to relieve the tension. So what are the causes of concrete damage? We have to think about these chemicals, obviously sulfates, abrasion, and mechanical damage, and even carbon dioxide from the air, from the atmosphere, the chloride ions. So when it comes to the chemical attack on concrete, especially when it comes to the bind as cement, the acids dissolves in the cement phase, and cement holds the concrete together. So obviously concrete will get disintegrates due to acids. And when it comes to sulfate attack, it's another critical aspect that sulfate reacts with the calcium aluminate in the cement, causes cement to expand and crack from inside. Because normally we get sulfate from groundwater. So this ettingrite formation causes expansive cracking. So it's a chemical formation, but it causes the cracks in the concrete. So when it comes to abrasion, due to the wind forces, due to the water damages, even for the friction, you get the direct physical damage of concrete due to abrasion. mechanical damages. This is the kind of the key point when it comes to the reinforced concrete, the passive layer. Now in fresh concrete, the steel is protected because it has high pH value of more than 13. So this forms a passive layer around the steel to protect it. Actually, we like designers, we all design for the concrete cover like 30 millimeter, 50 millimeter for the water retaining structures and all. But thing is, the newly poured concrete, fresh concrete, it has a pH of more than 30. So that is the protection we can get it from concrete to the steel. So for corrosion to occur, the passive layer must be destroyed. So I mean destruction of the passive layer. So when it comes to the stage one of the carbon dioxide attack on steel reinforcement, we call it carbonation. That is carbon dioxide from the atmosphere slowly penetrates the concrete, because as you all know, that is even with the 0.1 millimeter crack, the chloride ions and other ions will get absorbed to the structure. So it's from a front that moves close to the steel, follows through the cracks in the concrete, and it will reduce the pH of the concrete from 13 to 10. So now the pH value of the concrete is getting less now, getting reduced. So stage 2 in the carbonation, the front has already reached the steel. Now in the presence of moisture and oxygen, corrosion will start. So we all know that is corrosion to get start, we need oxygen and corrosion. I mean moisture. So once the front is already touched, the ions will touch the reinforcement bar, the corrosion will start. The chloride attack on steel reinforcement. Again, the chloride penetrates concrete through the cracks and pores and attacks steel. It will give the rapid loss of steel, not like carbonation. It will introduce corrosion pits. That is loss of structural integrity. Once the corrosion has started in the concrete, so you can see the rust has 8 times volume of original steel. That's why you can see the corroded reinforcements inside the concrete causes expansive forces, and which cracks and it will create the spall of concrete. So this is we would say that is the concrete cancer. Stage 1, you can see that is on your in the slide. Just you can't see any visible crack or corrosion spot. It's like it's a slight discoloration in the concrete, but this is stage 1. So stage 2, after some time, the corrosive agent has reached the steel surface. In the previous slides, you have seen that is the front has already touched the steel bar. Then you can see slight small patch of the corrosion, and it's a reddish corrosion patch. So after some time, spalling of the concrete cover to reinforcement steel is clearly visible. Now that is the stage 3. Of course, this is a stage 4. The severe spalling of concrete cover over the reinforcement steel is evident. So this is the carbonation. You can identify this with the picture. The entire reinforcement bar is like covered with the corrosion. So it's the front has already touched the reinforcement bar. Lack of cover. Again, lack of cover. So you can see this when it comes to the corrosion attacked by chloride. So you can see the corrosion pits, not like carbonation. The here and there, the small pits are visible. So this is the chemical attack. Construction and design, of course. Sometimes due to the lack of quality of the construction, sometimes the proper coverage is not provided. And even when it comes to the column heads and all, the workability, I mean the poor workmanship due to the lack of pokering or compaction, this will create the weak points in the concrete. So another concern we have to think about the structures in marine condition environment. So because this is like C5 environment, like highly corrosive. So we have to think about special concerns about the protecting the structures. Corrosion in the marine environment, like you can see this concrete in the tidal zone, because now where this the surface, because let's say we have a concrete, reinforced concrete, it's a pipe, because you can see that is the area between the tidal zone, low tide and high tide. That is the most vulnerable and most critical part we have to protect. Abrasion and chemical, because abrasion is also there, because with the waves and all, it will abrade the surface concrete, and chemical attack is also there, and very much the rich oxygen which in water. So all the elements which are very much hazardous to the structure will be there between the high tide and low tide, that is concrete tidal zone. So what we can do, because we talked about these honeycombs, defects, cracks, and the bad workmanship. So we have come across these tidal zones, the concrete piles or structures. We can do nothing for certain time, of course. We can keep our fingers crossed. Okay, we wait. Or downgrade of the function. Reduce the maximum loads. So as designers, you all know that is like we have some intended imposed load, so we reduce it. So we change it to the mezzanine floors, to the machine floors, to the some kind of office space. So that can be possible. And preservation of the current state. So we can keep it as it is, like apply some coating, or otherwise we can do improvement, strengthening, or refurbishment of the part of the or all the structure, or reconstruction of the part of all structure, or demolition of all the part of the structure. So we can have so many options based on the client's wish, based on the budget they have, based on the structural engineers analysis. We can do following points. Why do we repair concrete? To maintain integrity, increase load bearing capacity, of course, increase durability. If not repaired, even in Sri Lanka, we had some bad experiences. So this will happen, it will collapse. So factors to be considered when it comes to the repair: intended use, requirement, performance characteristics, and of course life expectancy of the repair. Like let's say if we design a building like let's say 50 years, 100 years, even that, if we need to do the concrete repair, so you can analyze what is the life expectancy you need for 5 years, 10 years, again another 50 years. So it depends on the budget you have. It depends on the other factors you can get it. That sometimes it may be the time, it may be the cost, it may be the some kind of let's say some instances you can see some buildings cannot be demolished because things due to regulations you can't put up the same building. You have to reduce the building lines and all. So those factors should be considered. Accessibility of the areas to be repaired, size of the areas to be repaired, then of course appearance of the repair. And when it comes to the analysis and investigation of the structure, we can do these delamination hammer test, potential mapping, chloride profiling test, UPV test, carbonation test. All the tests we can do, but because what we need is we have to check and we have to identify what is the exact condition of the structure. So we need to have those parameters, those inputs to do the correct analysis. Of course, then the structural engineers will come to the scene. They'll analyze the entire thing with the existing reinforcement. But what is this? If the client needs to have another flow, another improvement, so what should be the next level of reinforcement, the strength you need? So those analysis will come to the play. So when it comes to repair options, of course, conventional concrete is there because you can break it for the large areas. We can implant the reinforcement bars again. It's very messy wet works. Of course, you can do it. For high performance concrete, like our sponsor is having so many varieties of cement and all. Yes, of course, you can do the high performance concrete, sprayed concrete, polymodified mortars, fluid micro concrete, that is self-compacting concrete, rapid cure mortar, resin mortars, of course. The next generation of strength is composites, CFRP or GFRP. So this is the kind of evolvement, technologies involving the repair methodologies. When it comes to contractor selection, when it comes to the designers as consultants, you have to think about these pre-qualified contractors, must have manpower, visit previous works, tender to based on the recent comprehensive investigation. Sometimes we are investigating a structure, but due to the budgets and due to the various scenarios, various conditions, we keep it for another 1 year, we postpone it, and but we based on our analysis or the tender or whatever the BOQ, based on the previous analyzed report. So we have to check out the recent comprehensive investigation, because all the tests that we have done it 1 year back, not applicable and not validated to this date. And of course, you have to give the unit rate contract. This is much critical part when it comes to the contracts, because thing is like the repair area and the repair scope of the work. Actually, we cannot identify correctly at the BOQ stage, in the tendering stage. But if you go for the lump sum, it's very much critical when it comes to the completion of the job in a quality way. And because sometimes the structural engineer needs to have the best outcome from the repair. So when it comes to the not a clear aspect of the budget, the client will resist. So unit rate contract is the ideal solution. To get the best outcome from the repair, and client to have the high quality supervision. So the basic steps I'm going to talk about. The surface cleaning, of course, we need to have surface cleaning properly, either sandblasting, whatever the cup brushing. But surface preparation is another part. So we have to remove the loose concrete, disintegrate concrete, and seal preparation, because we all know that is all the carbon dioxide front and carbon ions and chloride ions and already attacked the reinforcement bars. So we have to clean it, or otherwise we have to replace it. Seal preparation. So seal protection options, we are thinking sink-rich coatings, we can have it, epoxy coatings, but we make sure that if you are using sink-rich coating or epoxy coating, those coatings have to be compatible with the repair mortar or the concrete. Because thing is, sometimes let's say we have some epoxy coatings, those are marine grade and those are not compatible with the repair mortars or concrete. So it will, as we all know, this epoxy is very shiny and very durable and very seamless products. So this epoxy, then you have a concern. We have to have the concern, the proper bonding between the coated reinforcement bar and the repair mortar. And cement epoxy coatings, polymodified cement slurries, zinc anodes, surface applied corrosion inhibitors, casting corrosion inhibitors like magnesium. Like the more active element we can attach to the steel, and drilled-in corrosion inhibitor. This is we can say there's migrated corrosion inhibitors. I'm going to talk about little bit of migrated corrosion inhibitors because it's a kind of not new technology. Because compared to other countries, Sri Lanka, it's kind of new. Of course, we can paint it and we can have the sink-rich primers or the reinforcements. When it comes to migrated corrosion inhibitors, so it has a work as a migration corrosion inhibitor by building a vapor density within an enclosed space. So what we have a small capsules like this, it quickly vaporizes inside the concrete, because we know that concrete is very porous. Porosity is there, and absorbs the steel surface within the close proximity. Like it's like 1 cube. We normally insert 1 capsule per cubic meter. blocking the path of chlorides, water, and oxygen, and fuels the steel corrosion. I mean, to reduce the corrosion, because things like chloride and water, oxygen, it will avoid, it will block the path to the reinforcement bar. So this is the mechanism, the steps. Like on your left, you can see that is first we have to drill it, just insert the capsule and plug it. It will do I mean, it will do his, their job. Because once the top figure you can see, figure 8 is, I mean, the cross section showing the expansion of corrosion on a steel reinforcement bar in concrete with 2% chloride. Once you scan it, so you can see the spread of the corrosion. But once you apply that particular vapor phase inhibitors, I mean migratory corrosion inhibitors, the cross section show it's the effect of the capsule. It's suppressing the steel corrosion by absorption to the structure surface. When it comes to priming options, of course, we can use for the repairs. We can use water, non-dispersible polymers like non-dispersible polymers, epoxies, polymodified cement slurries. And we can use the hand applied mortars for the little areas, sprayed concrete like shot treating for the big areas, foam and pour if you can have the self-compacting concrete, micro concrete, you can use the formwork. When it comes to curing options, again, you can use water and hessine. I mean, you can use polythene sheets, curing compounds, of course, protective coatings. And let's say we have to do a high-end and more critical repair with the concrete and reinforced concrete. Of course, if the accessible is not there, because if you are for the working platform, to the scaffoldings, what you do is like you invest in huge costs. So to protect the repair, you have to use some kind of high-end coatings rather than using protective coatings for the curing as well, because it will give the two aspects: curing plus the durability protection. We can use silent silexene, polymodified cementitious coatings like the 2K waterproof with Tokyo. The sponsor is having the polymodified cementitious coatings. So those are the protective coatings we need for the concrete repairs. And of course, when it comes to the aliphatic coating, because let's say the polymodified cementitious coatings need some kind of protection. Let's say we are doing a slab concrete repair, so over that we can use these polymodified cementitious coatings. But when it comes to these structures, like we have to open for the atmosphere, like the direct sunlight. So aliphatic acrylic coatings we can use, because aliphatic in the sense like it's 100% UV stable. Aliphatic terms, even epoxy and PU coatings, we have normally we go as the engineers, we always go for the PU coatings when it comes to the outside, I mean the exterior. So, but thing is that we have to concern about there are two types of PU are there. One is like aliphatic polyurethane, other one is aromatic polyurethane. So aliphatic polyurethane is 100% UV stable. So we have to go for the aliphatic polyurethane if you are going for the exterior harsh environments. So protection of repair and application procedure, like for the engineers who are like going to do these repair procedures, marking out, demarcation, because you can see that each and every any repair mortar in the any brand in the industry, they'll ask for the some kind of minimum depth to be poured, minimum depth to be have. I mean, if it is a mortar, you have to have a minimum depth. If it's a grout, it's a flowable thing, you should have a minimum depth. So that's why we need a demarcation.
Yes, we can see.
Okay. So still, when it comes to steel preparation, as I said, there is method such as wire brushing is not allowed. I mean, not effective, because thing is you can't completely remove the rust. Of course, otherwise we can use some kind of rust removers But we have to make sure that is when you are using rust removers are like slightly acidic components. I mean, slightly acidic base is there. So if you can thoroughly wash it with the fresh water, then of course acid washing. I mean, like using use of uh, 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 I mean, like corrosion inhibitors are good, but thing is like, but make sure better to use. The ideal one is go for the sandblasting. But when it comes to the replacement of the existing corrodor reinforcement, you have to think about the replacement because normally, as a practice, we go for the less than more than 20% of the diameter, effective diameter. We'll replace it, or advised by the structural consultants, we go for the the optimum and the replacement of the bars. What kind of materials to be used? Because if it's a small areas, we can go for the like hand patch repair mortars, medium size repair, pourable micro concrete. If it's a large repair, we have to do, we have to of course go for the spray. Hand compaction, I mean we have to finish it like this. And this is the pouring of micro concrete. It's like fluid micro concrete, self-compacting. These are the steps. Like shutter, prime substrate with water. You can see that is air releases are there on top. And draining, we remove the primers. I mean, the priming is done now. And we can, fluid repair compound, we can apply it with pressure, with the pressure grouting and finish it. So pressure grouting is like where the reinforcement are very congested, like you can see in the picture. So you have to go for the pressure grouting. This is another part. We talk about cracks as well in the concrete. Normally designers allow 0.2. Even if it's less than 0.1 millimeter, of course the chloride and iron ingress is there. So these are the typical basements. You can see the calcium leaching because through the cracks, the free calcium has come out. The leaks are there. The car parks, tunnels, deep shafts, basement slabs. So these are the places we can go for the crack injection. Substrate, the sheet piles. So normally what we can do is like when it comes to crack injection, we have to seal the crack parts. We have to inject from the bottom to the top. We have to fix the nozzles. So many mechanism. I mean the methodology is there, so you can identify those. This is the next. No, I can't say this is the next generation because these have been in the practice for more than like 30-40 years. But FRP strengthening of structure elements is like it's new thing. We don't need to go for the wet works, so it's very clean job in a rush at the because sometimes the client needs to have a additional flow, additional or they are changing the structure engineers changing imposed loads because they are using the changing their intended use of the building because the office floor may go to the factory floor, the mezzanine floor, even for the deteriorated structures, retrofitting. I mean, like it's an old structure. Sometimes you can't break it due to the building lines or the historic building. So we have to preserve this structure. So we can do wonders with FRP. I mean, fiber reinforcement polymers. So these are the requirements for the structures and damage old structures. New structures going significant design changes, as I said, under design structures. So why FRP? It's lightweight, easy to use. As I said, no wet work, about 5 times stronger than steel, high versatile, and of course the critical part when it comes to the corrosion resistive. We have type of fibers, carbon, aramid, glass, because these are serve different purposes. And when it comes to application material types, we can get unidirectional sheets, bidirectional sheets, and laminates. I mean, we can term it as plates, and even we can get carbon rods, fiberglass rods. So those are very much resistive to corrosion. So when it comes to FRP versus steel, I mean, FRP is having linear elastic behavior, no yielding, high ultimate strength, low strain at failure. So you can see its carbon fiber is like 2500 newtons per millimeter square, aramide, glass, and when it comes to laminate, so you can, because it's the normal laminates, the FRP plate is coming with the impregnated resins, the epoxies. So you can see steel is around 500. So we can do the applications texture, shear, confinement. So those are the applications we can have when it comes to FRP. FRP systems increase the ductility, of course. For the seismic retrofitting, we have to go for the glass fiber. When it comes to the explosions, protection against impact, like let's say some kind of the defense structures, when it comes to the bridges in a highway, so those are the fibers we can go for the aramide fiber. Those are the different materials, because actually when it comes to the, earlier we talked about concrete. Now we are concerning about the how to overcome weaknesses of the concrete. Like let's say we have reinforcement concrete. We know that is corrosion is very much, the reinforced concrete is vulnerable to corrosion. So now we are deviating from the material type we are using. Actually, this is the kind of repair. Concrete repair is like we are evolving with the material. So like we have glass, we have coatings, polyurethane, epoxies, so on. So actually, hello.
Yes, we can hear.
Yes, we can hear
Yes. So these are the parts. Then let's say when it comes to axial enhancement, so then we can go for the carbon. Flexural enhancements. We can go with the carbon. So these are the, with the structure engineer support, we can go for the negative moment enhancement, shear enhancements, positive moment enhancements for the sagging and hogging. And when it comes to flexure and shear reinforcement, of course we need to have the grinding of surface. The surface still, surface preparation is the key for the any epoxy or any material application. Carbon or whatever. Because reason is we have to make sure that we make a good anchor profile to transfer the strain and stresses to the carbon to the concrete. So even we can designers can design for the earthquakes. This is for the punch and shear. NSM in the sense near surface mounted carbon rods or carbon plates. So those are slots in laminates. You can see that is top of the slab. We can cut grooves. We can insert the carbon laminates to the groove, and that is called near surface mounted and pre-stressed laminates. Pre-stressing is, of course, we can see the other the next to this column. You can see the plates are mounted with the anchors. So that is actually to gain the additional load with the anchorage length. So those are the mechanisms and those are the designs you can do as structural engineers to the CFRP. So you can see this strength against punch and shear by using again near surface mounted and less anchorage laminates with plates. So now we talked about like, okay, there is good wonders we can do with carbon, we can do with FRP. But of course, the reason is like when it comes to the carbon only or glass only or aramide only, there's no warning before failure. Of course, we know that we use steel for so many years. We know that it will elongate and it yields and it gives some warning before collapsing. But when it comes to the other carbon, aramide, and glass, the brittleness is the more crucial. No warning before failure; it will suddenly collapse. But again, as structural engineers and all, you can design with the bigger, because we have a bigger leverage and bigger tolerance to do the design. Because when it comes to carbon 500, steel 500, of course you can go with the 4500 for the carbon even. and still evolving and under research and development, most of the application of the carbon fibers, I mean, glass fiber, whatever, FRP. Codes are not supporting full practical scenarios and need model testing. Because in the, like, let's say we normally use ACI code for the carbon designs, the structural engineers design with the ACI code. But sometimes the aspect ratio of more than let's say 2 columns are known. The guideline is not supporting. So then you have to go for the model tests. And even when it comes to Sri Lankan laboratories and institutes, we don't have much of testing facilities. So this is another part we have to develop when it comes to the FRP designs and FRP applications. And when it comes to the theoretical aspect of the carbon fiber, I mean FRP, all the FRP materials, like let's say even that is carbon or glass or aramid or the sheet or the thread, we are chemical anchors. We know epoxy is a very good, very versatile, very durable material with high strength. But we have to think about epoxy is vulnerable. You all can see my screen.
Yes.
Yes. So
Yes, we
about
can.
the relay, and this is like as we discussed, like the when it comes to the critical point, 1050 is it has to be the non-fire side. So it's a big task to do with the another aspect, like we have to go for the spray applied fire resistive materials like SFRM. That is, it's a term called SFRM. So SFRM undergoes significant expansion when heated, and it becomes an insulation. So that's right, because this is a collection of, now we are giving this, I mean, remedy or solution or whatever to mitigate the problems. Like we all know that is we need carbon fibers, so FRPs to get this more strength, to take the durability, or to make the repair in a good condition or in a good stage. But again, we have another problem to face in the fire resistivity. So again, then we have to go for another material. It's like cementatious fireproofing, gypsum based, vermiculite. So we have to go with that as well to protect our structure. I mean, the solution. I mean, we have to protect the structure, or to enhance the durability of the structure. We use fibers to protect the fibers from the fire. We have to use fireproofing materials as well. So this is the way, because once we install the carbon fiber or glass fiber, the application of the fire resistive material is very difficult. So then we have to use the glue, epoxy glue pins. Then around 2-inch thick insulation materials we have to spray on top of the carbon fiber. So I'm touched a little bit of marine structure repairs. The reason is like it's very much vulnerable in the tidal zone. So we have bridges to sea walls to protect. This, when you come to building materials, we have wood, but of course not much popular in Sri Lanka. But of course we have wood piles, concrete steel, and it will damage with chloride abrasion, wetting and drying cycles in the tidal zones. So what causes deterioration? Of course, concrete, chloride chemicals, internal metal corrosion. When it comes to steel, salt spray. So we can use epoxy grout for pile repairs. So basically we have to think about that only. So we can use the jackets, the fiberglass jackets after the surface preparation. just fill the fiberglass jacket with towel grade epoxies. So these are the like before in the marine structure. After removal of poly jackets and cleaning, we can install the jacket, fiberglass jacket, and we can fill it epoxy grout. These are job site photos. Now this is actually the Sri Lankan project. So we have for the flexure, for the bending and all, used carbon laminates, and this is a column confinements. And because you can see on your right, the picture is like after installing the carbon fiber sheets, they have put up the sand blinding. We have put up sand blinding to cover it up the aesthetic finish with the after the putty and all. So these are the column carbon fiber wrapped. So these are the steps. First, we have to check the grinding, surface preparation to get the anchor profile. Check the levels. And if the cracks are there, crack injection works has to be done. And installation of carbon sheets. Marine structure, this not in Sri Lanka, these small leaves. So these are the honeycomb areas, and you can see the bottom picture, the migratory corrosion inhibitor capsules we can use, grinding, inserting of migratory corrosion inhibitor capsules, epoxy bonding and repair, use of glass fiber to take the durability, and sand blinding. And thank you very much.